So now that we've identified what a linear relationship looks like, what a quadratic relationship looks like, and what an exponential relationship looks like, we are going to take a look at some data tables, and we're going to see if we can identify those relationships. So we're playing a little game here called linear or not. So we're trying to identify a linear relationship. And remember that a linear relationship has a common change. So we're changing the same distance for our change in our y value divided by our change in our x value. And remember, that's called the slope. So to identify a linear relationship, we want to see the same value for every time for that change in y over change in x. So let's take a look at some of these. All right, so let's look at table A. So for table A, we have a constant change in our x values, right? Plus 1, plus 1, plus 1. That's easy. However, over here in our y value, we have plus 5, plus 7, plus 9, and plus 11. So we definitely do not have a linear relationship in table A. If we want to dig a little deeper, if you remember back to our quadratic relationships, we can find a second difference. And notice that our second difference is consistent. It's always going to be plus 2. So table A is actually a quadratic relationship. Now, it's great if you can identify that as a quadratic relationship, but really we're just talking about, is it linear or not? All right, let's look at table B. So for our x values, here we've got plus 2, plus 4, plus 6. So we've got some changes in our differences for the x value. Now, that doesn't mean we're going to necessarily not have a linear relationship just because we have differences in our x values. We have to compare them to the changes in our y values. So for the first change in our y value, we go from 7 to 10, we're adding 3. Here we're adding 6. Here we're adding 16 to 25. We're adding 9. And here we're adding 25 to 37, 12. Great. Okay. So let's compare our change in y over change in x. So here we have, for our first change in y, we have 3. For our first change in x, we have 2. For our second change in y, we have 6. And our second change in x, we have 4. We have our third change in y, we have 9. And our change in x for that is 6. And finally, we have 12 compared to 8. Now, I want you to notice something about these fractions. If you notice something about equivalent fractions, these are all equivalent fractions. We can simplify all of these fractions to be 3 over 2. So we have 3 over 2. We can also divide the top and the bottom by the same number. Doesn't have to be the same number in each fraction, but the top and the bottom have to be divided by the same number. And when we do that for each of these fractions, we get a common fraction, which is 3 over 2, an equivalent fraction. And so we have a similar, or we have the same slope. We have the same change in y over change in x. And so this is indeed a linear relationship. Let's take a look at table C. So here we have, let's look at our x, change in x. So we're adding 1, adding 2, adding 4, and adding 8. On this side, we're adding 3, adding 6, adding 12, and adding 24. All right. Let's take a look at, let's take a look at our change in y compared to change in x. Okay, so here we have 3 over 1, 6 over 2, 12 over 4, and 24 over 8. And what I notice again is we have some equivalent fractions. So we can divide the top number by the same number, top and bottom by the same number. For 12 over 4, we're going to divide the top and the bottom by 3. For 24 over 8, we're going to divide the top and the bottom by 4. By 8. And I misspoke here too. For 12 over 4, we're going to divide the top and the bottom by 4. And for 24 over 8, we're going to divide the top and the bottom by 8. And each time we end up with 3 over 1, which is the same as 3. So we have the same slope each time. So we have a constant rate of change. So this is indeed going to be a linear relationship. This video is getting a little long, so I will stop here and continue with D, E, and F in a future video.